Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module An Overview of Thermodynamics Part 2 from paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We are going to describe evolution of thermodynamic potentials, which are most important thermophysical entities to know the equilibrium state of the system. Apply mathematical apparatus of Legendre transformations, partial differentiations, and Jacobian determinant to derive various thermodynamic relations. Define repeatedly encountered measurable physical quantities like heat capacity at constant volume and pressure, isothermal and adiabatic compressibility, coefficient of thermal expansion and susceptibility. Starting from various thermodynamic potentials, derive generic equations of state. Derive famous Maxwell's relations to link non-measurable thermodynamic quantities like entropy with measurable thermodynamic quantities like temperature, pressure, and volume. Describe the important extremum principles of entropy, internal energy, and thermodynamic potentials to characterize equilibrium state of a system. Interpret concavity principle of entropy and convexity principle of internal energy geometrically and see their physical significance. Derive stability criterion for a system in equilibrium and use these criterion to arrive at system-independent results that heat capacity at constant volume and constant pressure, adiabatic and isothermal compressibility are always greater than or equal to 0. Prove using stability criteria that specific heat at constant pressure is greater than or equal to specific heat at constant volume. Thermodynamic potentials have unit of energy and their minima gives the equilibrium state of the system subject to constraints. We confine ourselves only to those thermodynamic descriptions which shall later be needed in the study of statistical mechanics. This module has been developed for postgraduate level as per the following subtopics: thermodynamic potentials, Maxwell relations, thermodynamic relations, applications of Maxwell's relations, extremum principles, beyond thermodynamics. Let us focus our attention on thermodynamic potentials. Let us recapitulate. In previous module, we saw that out of the given thermodynamic variables entropy S, internal energy U, volume V, and number of particles N, to have energy representation, we treated U, the internal energy, as a function of entropy S, volume V, and number of particles N. That is, S, V, and N were treated as independent variables. For entropic representation, we treated S as a function of internal energy, volume, and number of particles. That is, U, V, and N were treated as independent variables. We also observed another thing there, that in these two representations, independent variables were extensive parameters and independent variables turned out to be partial derivatives of a dependent extensive variable with respect to independent extensive variable, keeping other independent extensive quantities constant. Furthermore, it is always desirable to have independent variables as those quantities which are easily measurable, for example, temperature T and pressure P. Also, it is worth noting that temperature T is a partial derivative of internal energy U with respect to S. That is, T is equal to partial derivative of U with respect to S at constant volume and constant number of particles. And pressure P is a negative partial derivative of internal energy U with respect to volume. That is, P is equal to minus of partial derivative of U with respect to V at constant S and constant N. So in other words, we are looking forward to functions of independent variables which may be intensive variables like P and T. For a function of a single variable f is equal to fx, this amounts to saying find a function psi which is a function of derivative of f, that is psi is equal to psi as a function of df upon dx. It is like saying that we wish to generate a function which is a function of the slope of the tangents drawn at each point. This is performed by the famous Legendre transformations. Seeing the importance of Legendre transformations, it's worth having a digression on these. Legendre transformations provides us a way to convert one thermodynamical potential into another with a difference. In thermodynamics, Legendre transform involved is negative Legendre transform compared to when we use it in classical mechanics. First, we shall look at it from the point of view of single variable function fx, whose Legendre transform we are seeking. Legendre transform produces from fx a new function hp involving a change of variable from x to p, where p is equal to derivative of f with respect to the variable x. The new function hp has the same information as fx, so that it can be transformed back. The steps are: start with fx, find df by dx, then Legendre transform of fx is maximum over x of fx minus px, where x is a value that maximizes Legendre transformation of fx for a given p. This procedure can be extended to a multivariate function fx yz, as is the case with thermodynamics. Hence, we can define Legendre transform of fxyz with respect to x equal to maximum of fxyz minus px over x, where x is the value that maximizes Legendre transform of fxyz with respect to x for a given p. For example, Helmholtz free energy FTVN is Legendre transform of internal energy U as a function of SV and N. We can write FTVN is equal to Legendre transform of internal energy U with respect to S as equal to U minus S multiplied by derivative of U with respect to S at constant V and N, which becomes equal to U minus ST. Furthermore, Gibbs free energy or thermodynamical potential GTPN can be derived as Legendre transform of Helmholtz free energy capital F TVN involving a change of variable from V to P. That is, Legendre transform of FTVN with respect to V is in fact Legendre transform of FTVN with respect to V is equal to Legendre transform of U with respect to S. Once again, Legendre transform of this with respect to V, which is equal to Legendre transform of F with respect to V is equal to F minus V delta F by delta V at constant temperature and number of particles is equal to U minus Ts plus PV. Let us now try to enumerate various thermodynamical potentials which we encounter in statistical physics and in thermodynamics. Let us start with internal energy U, which is a function of S, V and N, such that du is equal to TdS minus PdV plus PdN. We note that there are three pairs of variables occurring here, leading to 2 raised to the power 3 different thermodynamic potentials. Each additional pair of variables doubles this number. Let us look at another du encountered in module 5. Du is equal to TdS minus PdV plus mu dN plus V, where V here is velocity, and dP, P where is momentum, plus omega dl plus E dP, where E here is electric field and P is the polarization, plus HdM. It contains 7 pairs of variables and hence could lead to 2 raised to the power 7, that is 128 thermodynamic potentials. This is indeed a mind-boggling number. However, we shall concentrate only on the equation with 3 pairs of variables and generate 8 thermodynamic potentials. Out of these 8 potentials, the first 5 are well known. Here I am interested in giving you a glance of the thermodynamic potentials which we encounter in thermodynamics and statistical mechanics. The first 5 thermodynamic potentials which we are going to use in statistical mechanics are internal energy, free energy, enthalpy, Gibbs free energy, and grand thermodynamic potential. The other 3 thermodynamic potentials which we can define have no special names. If you have a look at this table, you will find internal energy as a potential has a dependence on 3 variables S, V and N. Free energy, which we sometimes also call as Helmholtz free energy, represented by capital F, is dependent on 3 variables T, V and N. Enthalpy, which we are represented as capital H here, is dependent on S, P and N. Gibbs free energy, which we are represented with capital G, is having dependence on temperature, pressure and number of particles. And grand thermodynamical potential, which we are representing by phi, has got 3 independent variables: temperature, pressure and chemical potential. The other 3 thermodynamic potentials respectively have their dependence on 3 variables S, V and mu. The second one has got dependence on S, P and mu, and the third one has got dependence on T, P and mu. It is worth keeping this set of relationships in mind to be comfortable in applying these relations later in statistical mechanics. You must be wondering, how come one is going to remember this table? Indeed, it is very easy to learn this table, provided we recognize that independent variables in the last column are those variables which appear on the right hand side in the third column as full differentials. This is done through Legendre transformation. The trick is, let us start with first pair of variables Ts. We can write du minus dTs equal to minus Tds minus sdt plus Tds minus dV plus mu dN, which can further be written as u minus Ts is equal to minus sdt minus pdV plus mu dN, which can be further written as dF is equal to minus sdt minus pdV plus mu dN. Following these steps gives us a Legendre transformed function f called Helmholtz free energy, which now has T as the independent variable instead of S. The grand thermodynamic potential phi can be obtained by 2 successive Legendre transformations over 2 pairs of variables Ts followed by mu n. Similarly, other thermodynamic potentials can be obtained. Also note that a thermodynamic potential is minimum if dF is equal to 0, where F is any of the defined thermodynamic potentials. For example, enthalpy H is minimum if dH is equal to 0, which happens only if ds is equal to dP is equal to dN is equal to 0. That is, when the entropy is constant, pressure is constant, and number of particles remain constant. This means that enthalpy describes a closed, isobaric, and adiabatic collection of particles. Thermodynamic potential phi describes an open, isothermal, and isobaric collection of particles. Now, it will be worth understanding how these thermodynamic potentials can lead to equations of states. We are now armed with the knowledge of these thermodynamic potentials, out of which we focus on the 5 thermodynamic potentials only, that is, internal energy, Helmholtz free energy, enthalpy, Gibbs free energy, and thermodynamic potential phi. We can get in each of these representations equations of states. For example, in the case of internal energy as a potential, whose total differential du is equal to Tds minus Pdv plus mu dn, equations of state are T is equal to delta U by delta S at constant V and N, P is equal to minus delta U by delta V at constant S and N, mu is equal to delta U by delta N at constant S and V. In other words, we have been able to write temperature as a function of SV and N, as a function of SVN, and chemical potential as a function of SVN. Similarly, for Helmholtz free energy and enthalpy, you can write down the corresponding equations of states. Similarly, in the case of Gibbs thermodynamical potential, of Grand thermodynamical potential, we can write down the corresponding equations of state. In the case of Gibbs thermodynamical potential, the equation of states which we get are functions of T, P and N for entropy, volume, and chemical potential. Similarly, in the case of Grand thermodynamic potential, we get equations of states involving S, V and N respectively, such that S is a function of T, P and mu, V is a function of T, P and mu, and N is a function of T, P and mu. Now let us look at famous Maxwell relations. In fact, here we would like to appreciate the generation of thermodynamic potentials. Maxwell's relations are very interesting relations, providing a link between measurable quantities like pressure P, temperature T, and volume V, which can be measured directly, and non-measurable quantities like entropy S, enthalpy H, Helmholtz free energy F, and Gibbs free energy G, which cannot be measured directly. Therefore, it is crucial that we express non-measurable quantities in terms of measurable quantities. Maxwell's relations provide us exactly this option. By choosing any two independent variables and taking mixed derivatives of a given thermodynamic potential with respect to these, and remembering that order of derivative does not affect the mixed derivatives, leads to what are known as Maxwell's relations of thermodynamic potentials. Realizing the fact that we need to make a connection between measurable quantities and non-measurable quantities, we can write Maxwell's relations involving the 5 thermodynamic potentials which we have learnt about. For example, the following table gives us Maxwell's relations derived from internal energy. This table gives us Maxwell's relations derived from Helmholtz free energy. This table gives us Maxwell's relations derived from enthalpy. This table gives us Maxwell's relations from Gibbs thermodynamical potential. This table gives us Maxwell's relations derived from Grand thermodynamic potential. Before we move further to discuss thermodynamic potentials and ensuing Maxwell's equations, it will be handy to define some thermodynamic relations which provide measurables for a given thermodynamic system and also help us measure the unmeasurable quantities encountered in thermodynamics, such as entropy S and chemical potential mu. Let us understand the relations corresponding to a very interesting physical quantity called heat capacity. Heat capacity of a system is defined as amount of heat required by the system to change the temperature of the system by unity. We can write this mathematically as at constant x, say volume V or pressure P, keeping mass or number of particles constant, Cx is equal to limit delta T approaching 0, delta Q by delta T is equal to T times partial derivative of entropy with respect to temperature at constant x and number of particles n. The above relations can be related to change in internal energy, provided volume is kept constant, or change in enthalpy, provided pressure is kept constant. It is known to us that du is equal to Tds at constant volume and number of particles, and dH is equal to Tds at constant pressure. Therefore, we have Cv is equal to T delta S by delta T at constant V and N is equal to delta U by delta T at constant V and constant N. Cp is equal to T delta S by delta T at constant P and constant N is equal to delta H by delta T at constant P and N. Compressibility is also a very interesting measurable quantity. Compressibility of a system Kx is defined as the ratio of fractional change of volume to applied pressure on the system. We can write it as Kx is equal to limit delta P approaching 0 minus delta V upon V divided by delta P at constant x and constant number of particles is equal to minus 1 upon V delta V upon delta P at constant x and number of particles, where x is equal to T implies that pressure was applied under isothermal conditions and x is equal to S implies that pressure was applied under isoentropy conditions. Therefore, it becomes respectively isothermal compressibility and adiabatic compressibility. Negative sign shows that volume compresses as pressure is applied. Let us have a look at another measurable quantity, coefficient of thermal expansion. Coefficient of thermal expansion alpha P is defined as the fractional change in volume per unit change in temperature under constant pressure and constant number of particles. We can write it as alpha P is equal to 1 upon V delta V upon delta T at constant pressure and number of particles. Susceptibility. This is another measurable quantity which we need when we apply an external field to the system. Under the influence of an external field H, an isotropic magnetic system at constant temperature or constant entropy acquires a magnetic moment M. The isothermal and adiabatic magnetic susceptibility can then be defined as chi T is equal to delta M by delta H at constant temperature, or what we call isothermal magnetic susceptibility, and chi adiabatic is equal to delta M by delta H at constant S, the adiabatic magnetic susceptibility. Now we will focus our attention on the application of Maxwell's relations and how they help us to relate measurable quantities with immeasurable quantities. Following table gives us a list of measurable and non-measurable thermodynamic quantities. And one can very interestingly see that the list of measurable quantities needs to be related with the non-measurable quantities which we encounter in thermodynamics and statistical physics. Let us look at variation of entropy with pressure in terms of two measurable quantities alpha P and V. We start with relation delta S upon delta P at constant temperature and number of particles is equal to minus delta V upon delta T at constant pressure and constant number of particles. If we start from the left hand side, we can write delta V upon delta T is equal to 1 upon V into delta V upon delta T at constant pressure and number of particles multiplied by V, which is equal to alpha P into V. Therefore, change of entropy with pressure at constant temperature and number of particles is a product of alpha P and V with a negative sign. Let us look at now variation of entropy with volume in terms of measurables alpha P and Kt, where alpha P is coefficient of thermal expansion at constant pressure and Kt is isothermal compressibility. Now we start with the Maxwell relation. Delta S upon delta V at constant temperature is equal to delta P at with respect to T at constant volume, and using the trick 4 of differentiation given in the appendix of the e-text, we have delta P upon delta T at constant volume is equal to minus delta P upon delta V at constant temperature multiplied by delta V upon delta T at constant pressure is equal to V into delta P upon delta V at constant temperature multiplied by 1 upon V into delta V upon delta T at constant pressure is equal to 1 upon V delta V upon delta T at constant pressure divided by minus 1 upon V delta V upon delta P at constant temperature, which is equal to alpha P upon Kt, the ratio of coefficient of thermal expansion to isothermal compressibility. Therefore, delta S upon delta V becomes equal to alpha P upon Kt. There is another relation which becomes very handy when we will be doing some systems later in statistical mechanics. It involves ratio of heat capacity at constant volume and heat capacity at constant pressure in terms of ratio of isothermal compressibility and ratio of adiabatic compressibility. Let us recall the definition of Cp and Cv. We can write Cp upon Cv is equal to delta S upon delta T at constant pressure and number of particles divided by delta S upon delta T at constant volume and number of particles, which can be written as equal to minus delta P upon delta T at constant S and N divided by delta P upon delta S at constant T and N divided by delta V by delta T at constant S and N divided by delta V by delta S at constant T and N using thermodynamic relations, which when solved gives us Cp upon Cv as the ratio of isothermal compressibility to adiabatic compressibility. Let us also look at another interesting result: difference between heat capacity at constant pressure to heat capacity at constant volume. This involves usage of Jacobian determinant in one of the Maxwell's relation. Starting from the definition of heat capacity at constant volume, Cv upon T is equal to delta S upon delta T at constant volume and number of particles, and using the definition of Jacobian, it can be written as delta SV over delta TV, the Jacobian, is equal to delta SV over delta TP is equal to delta TP over delta TV. Now, recalling the expanded definition of Jacobian, this can be written as Cv upon T is equal to delta S upon delta T at constant pressure multiplied by delta V upon delta P at constant temperature minus delta S upon delta P at constant temperature multiplied by delta V upon delta T at constant pressure, and whole of this difference multiplied by delta P upon delta V at constant temperature, so that Cv upon T is equal to delta S upon delta T at constant pressure minus V into delta S upon delta V at constant temperature multiplied by 1 upon V into delta V upon delta T at constant pressure, or Cv upon T is equal to Cp upon T minus V into delta S upon delta V at constant temperature multiplied by alpha P. Using Maxwell's relation, delta S upon delta V is equal to T is equal to delta P upon delta T at constant volume, and as proved earlier, we get delta P upon delta T is equal to alpha P upon kT. Hence, the difference between heat capacity at constant pressure to heat capacity at constant volume can be obtained very easily as Cp minus Cv is equal to Tv alpha P square upon kT. This is a very interesting relationship. Firstly, it proves that Cp is greater than Cv. Secondly, it is true for any thermodynamic system because it has not assumed anything about the composition of the system, revealing the universal sweep of thermodynamics. Now, let us learn about extremum principles in thermodynamics. Principle of maximum entropy for equilibrium. This principle characterizes the state of equilibrium as the state of maximum entropy for a given value of internal energy U, volume V, and number of particles N, or any other extensive parameter involved in the system. Mathematically, this means ds is greater than or equal to 0 and d2s is less than 0. Equality here implies that system is in equilibrium. Principle of energy minimum for equilibrium. According to this principle, for a constant value of entropy, equilibrium state is characterized by a state of minimum energy. Mathematically, this means that differential of internal energy is less than or equal to 0 and second order differential of internal energy is greater than 0. This principle is equivalent to principle of maximum entropy for equilibrium. Extremum principle for thermodynamic potentials. Many a times in thermodynamics and statistical mechanics, we have to deal with fundamental relations in Helmholtz free energy, that is F is equal to F as a function of T, V and N representation, enthalpy, that is H is equal to H as a function of entropy, pressure and number of particle representation, and gives free energy G as a function of temperature, pressure and number of particles representation. A natural question to ask is, what is the stability criteria for these thermodynamic potentials? Let us look at the stability condition Helmholtz free energy, which is a function of T, V and N for a constant value of V and N for the given system. The energy conservation law of thermodynamics implies that delta U is equal to delta Q. Since we know that delta Q is less than or equal to T delta S, we can write the above relation as delta U is less than or equal to T delta S. If in a process T is held constant, delta U minus Ts is less than or equal to 0. This equation implies that in a process in which T, V and N are held constant, Helmholtz free energy F is equal to U minus Ts is minimum. Similarly, one can prove that if in a process Sp and N are held constant, then its enthalpy has a minimum value. For all processes for which T, P and N are held constant, then the Gibbs free energy has a minimum value. It is interesting to note that for a system in equilibrium under constancy of respective variables, these functions have a minimum value, hence these are called thermodynamic potentials. Let us look at concavity principle of entropy. Assume that we have two systems in equilibrium. Such entropy of each system is a function of its extensive variables, S as a function of U1, V1, N1 and S as a function of U2, V2 and N2. Suppose that we bring these two systems together by removing the barriers or walls between them. The extensive parameters of the composite system will then be U1 plus U2, V1 plus V2, N1 plus N2 and so on. This combined system will not be in equilibrium, and its various parts shall tend to exchange energy in order to come to equilibrium. In this process of establishing equilibrium, since entropy cannot decrease, system must move to increased entropy, so that mathematically this implies entropy as a function of u1 plus u2, v1 plus v2, n1 plus n2 must be greater than or equal to entropy as a function of u1, v1, n1 and so on, plus entropy as a function of u2, v2 and n2 and so on. To appreciate geometrical meaning, let us cause a transformation of extensive variables on the left hand side such that u1 is equal to lambda u1 dash, v1 is equal to lambda v1 dash, n1 is equal to lambda n1 dash, and u2 is equal to 1 minus lambda u2 dash, v2 is equal to 1 minus lambda v2 dash, n2 is equal to 1 minus lambda n2 dash and so on, where lambda lies between 0 and 1. Then we get S as a function of lambda u1 dash plus 1 minus lambda u2 dash, comma, lambda v1 dash plus 1 minus lambda v2 dash, comma, lambda n1 dash plus 1 minus lambda n2 dash is greater than equal to S as a function of lambda u1 dash, lambda v1 dash, lambda n1 dash and so on, plus S as a function of 1 minus lambda u2 dash, 1 minus lambda v2 dash, 1 minus lambda n2 dash and so on. Or using property of extensivity, we have S as a function of lambda u1 dash plus 1 minus lambda u2 dash, comma, lambda v1 dash plus 1 minus lambda v2 dash, comma, lambda 1 n dash plus 1 minus lambda n2 dash and so on, greater than equal to lambda S as a function of u1 dash, v1 dash, n1 dash plus 1 minus lambda s u2 dash, v2 dash, n2 dash. Here, left hand side represents value of s at a point denoted by lambda u1 dash plus 1 minus lambda u2 dash, comma, lambda v1 dash plus 1 minus lambda v2 dash, comma, lambda n1 dash plus 1 minus lambda n2 dash, so on, whereas right hand side denotes a point on the straight line joining points s as a function of u1 dash, v1 dash, n1 dash and so on, and s as a function of u2 dash, v2 dash, n2 dash and so on. Pictorially, this is represented in the figure, and we notice that a point on a chord always lies below the point on the curve joining the 2 points, hence the name concavity principle of entropy. Now let us look at convexity principle of internal energy. In terms of energy representation, the energy minimum principle du is less than equal to 0 implies that u as a function of extensive variables s, v and n implies that u as a function of lambda s1 dash plus 1 minus lambda s2 dash, comma, lambda v1 dash plus 1 minus lambda v2 dash, comma, lambda n1 dash plus 1 minus lambda n2 dash and so on is greater than equal to lambda u as a function of s1 dash, v1 dash, n1 dash plus 1 minus lambda u, s2 dash, v2 dash, n2 dash and so on. This is represented geometrically in the adjoining figure, where we notice that a point on a chord always lies above the point on the curve joining the 2 points. Now we will look at the physical significance of these stability criteria. Let us discuss this stability criteria in terms of second derivatives of thermodynamic potentials with respect to their extensive and intensive parameters. In terms of internal energy, it implies that d2u exists, then d2u is greater than equal to 0. That is, delta 2u by delta s square at constant volume ds square plus 2 times delta 2u by delta s delta v ds dv plus delta 2u by delta v square at constant s dv square is greater than equal to 0. Using the values of the first derivatives, it reduces to delta t by delta s at constant volume ds square plus 2 times delta T by delta V at constant S ds dV minus delta P by delta V at constant S dV whole square is greater than or equal to 0. If this equation can be recast as ax square plus by square, then it will be positive definite if both a and b are positive. Therefore, we visualize the above equation in the form ax square plus 2bxy plus cv square greater than or equal to 0, where a is equal to delta T by delta S at constant volume, b is equal to delta T by delta V at constant entropy, c is equal to minus delta P by delta V at constant entropy, and recast it as ax square plus by square greater than or equal to 0, which can be done by simple mathematical manipulation as the following inequality: a times x plus b upon a y whole square plus c minus b square by a y square greater than or equal to 0. Note, since a is equal to delta T by delta S at constant volume is always positive definite, it implies that c minus b square upon a greater than or equal to 0, that is, b square is less than or equal to ac. This further implies that c is greater than or equal to 0. This leads to following three conditions. First, delta T upon delta S at constant volume is greater than or equal to 0. Delta T upon delta V at constant S is greater than or equal to 0. And delta T upon delta V whole square at constant S is less than or equal to delta T upon delta S multiplied by negative of delta P upon delta V at constant S, which further implies that negative of delta P upon delta V at constant S is greater than or equal to 0. That is, delta P upon delta V at constant S is less than or equal to 0. These three conditions have great physical significance and lead to following four results, which are independent of the composition of the system. Number 1, heat capacity at constant volume is always positive. Since delta T upon delta S at constant volume is greater than or equal to 0 and temperature T is greater than or equal to 0, therefore T multiplied by delta S by delta T at constant volume is greater than or equal to 0. Recalling the definition of heat capacity, this means Cv is greater than or equal to 0. Second, adiabatic compressibility cannot be negative. Note, since delta P upon delta V at constant S is less than or equal to 0 and V is always positive, V delta P upon delta V at constant S is less than or equal to 0, implying 1 upon Ks, that is adiabatic compressibility, is less than or equal to 0. That is, adiabatic compressibility Ks is always greater than or equal to 0. Third, isothermal compressibility is also always positive. Recalling, delta T upon delta V whole square at constant S is less than or equal to delta T upon delta S at constant volume multiplied by minus delta P upon delta V at constant S, and using the Maxwell relations we have minus delta T upon delta V at constant S multiplied by delta P upon delta S at constant V plus delta T upon delta S at constant V multiplied by delta P upon delta V is less than or equal to 0, implying delta T P upon delta SV is less than or equal to 0 in Jacobian terms, which can be further written as delta T comma P delta T comma V divided by delta T comma V multiplied by delta S comma V less than or equal to 0, which implies delta P upon delta V at constant temperature multiplied by delta T upon delta S at constant volume is less than or equal to 0. Since delta T upon delta S at constant volume is positive, the other factor on the left hand side must be negative. That is, delta T upon delta S at constant volume is less than or equal to 0. Multiplying with minus V and taking the reciprocal, we get isothermal compressibility greater than or equal to 0. Fourthly, Cp is greater than or equal to Cv. Recall that Cp upon Cv is equal to Kt upon Ks is greater than or equal to 0. Therefore, Cp upon Cv is greater than or equal to 0 and hence Cp is greater than or equal to Cv. So, learners, let us see what is beyond thermodynamics. Indeed, thermodynamics offers very powerful tools for calculating macroscopic properties of a system, howsoever complex the system may be. However, its basis is purely phenomenological and requires empirical inputs to set up the fundamental relations. The biggest limitation is that it does not consider the structure of matter or system at hand while describing the properties of macroscopic systems. This is exactly where statistical mechanics takes over and starts from the microscopic entities making the matter, and through average behavior of these large number of particles in a system arrives at fundamental relations which can be manipulated to get all other thermodynamic properties subject to experimental verification. So students, let us now summarize what we have learnt in this module. In this module, we have learnt to systematically generate thermodynamic potentials, to derive equations of state in different thermodynamic representations, that how by applying Legendre transformations thermodynamic potentials can be obtained, to write thermodynamic potentials in differential form, to derive Maxwell's relations, that Maxwell's relations provide a way to link non-measurable physical quantities with measurable physical quantities, the extremum principles for entropy, internal energy, and thermodynamic potentials for a thermodynamic system to be in equilibrium, stability criterion and their geometrical interpretation in the form of concavity principle of entropy and convexity principle of internal energy, that stability criterion in differential form reveal the global nature of the properties of heat capacities, that is, heat capacity at constant pressure and heat capacity at constant volume, compressibilities, that is, compressibility at constant entropy and compressibility at constant temperature, and thermal expansion alpha p, that they are always positive. The need to go beyond thermodynamics to understand properties of a system from microscopic conditions. Thank you.